Hello everyone. Hi Rohi. Believe we can start. So let me just share my screen and I'm going to do a run all first so that just give me 2 minutes so that I can run all the cells and then we'll give it a start. Okay? Hi Sarangs.
Hi, Mohammed.
Okay, I believe the cells have run. Yes. Okay, then let's continue. So yesterday, until yesterday, we have looked into one quick label encoding example. And then we have fit the model. We have seen how we can use it to fit the model. That's one thing that we have done. So now what we are going to do is that we are going to look into the next set of examples. When what we are going to do here is, let me just create a new section and I'm going to call this 10 usage of no, should I be calling this, because I've already taken a section with categorical. Give me a minute. Yeah, effects of categorical variable. Yeah. So I'll just continue writing like this, that now that we have seen the effect of label encoding on regression analysis use case, like the one above, we can see examples of one hot encoding as well, and how we can apply the same to perform regression analysis, right? So this is just a background note, or uh, right. So what we are going to do, similar to yesterday, we are going to let's say we'll now create another categorical variable, right? And later perform one hot encoding on this feature. Okay, so what I'm going to do, let's say just for the sake of simplicity, we'll create one variable where we have only two values. But as I've already told you, this apply no, I'm sorry, we'll create a variable where we have three values. Okay, so we will have three values, and then we are going to do the one hot encoding using the techniques which are available to us. So We'll try to skip the manual method now. We'll go with pandas first, then we can also quickly see how to do it with scikit-learn also. But as you have seen yesterday, I don't really recommend doing this kind of encoding using sklearn, because it's very difficult for you yourself to ascertain what kind of encoding values or what kind of labels for the encoding is what is being chosen by sklearn, if you know what I mean. So if you see yesterday also, we saw that it chose exactly the opposite that I have chosen. But I was able to figure that out, but only because I was able to figure that out only because I have done the manual label encoding first, and then I was able to compare the manual with the automated ones, and then I came to know that okay, this is the difference. Had it been the case, I would have directly done an sklearn encoding. I wouldn't have come to know, right? So that's why maybe as of now we can skip it, but at a later stage I'll also share you the documentations which you can go through, or maybe we will obviously be looking into examples later on when we do let's say case studies, right? So let's try to add this new column. What we are going to add this new column for is, let's say we are going to add this new column for the targeted geography. Okay, so we are going to add yet another new column called the targeted geography. Let me just write it over here. So now let's consider another categorical field or feature called targeted uh, or geography. Okay, targeted geography, which will have values of geographical categorization of where our customers, okay, our customers reside, right? So for example, uh, or yeah, I mean, let's say, so if we are doing or where our customers reside is not the right statement, maybe I'll say where our investments reside. Okay, and I'll also explain this. So what I'm going to do, we are going to add this new column, right, which is going to define whether we are making these investments on advertisement in the rural area, in the urban area, in the suburban area, and so on. And then we are going to see what is the kind of effect that it is having on our model, right? But this column is not there in the data. So similar to yesterday, we are going to create a dummy column with the dummy value. So let's set the seed. We're going to again set the seed, right? np.random.seed. I'm going to say 1, 2, 3, 4, right? And then I'm going to create this new column. Let me just scroll it above. Now what I'm going to do, assign the random numbers and use it to create the range of values. Okay, so what I'm going to do now, I'm going to do things a bit quicker because we have already done this earlier. It is just the extension. So what I'm going to do again, I'm taking the same variable name because it doesn't really matter for me. So the np.random.rand. Okay, so this is the function. I'm going to generate data with the length of advertising data set. So I took len advertising as the input. Now what I'm going to do, I'm going to again create a mask of nums, and this will be or maybe what I'm going to do is that, let's say, let's decide the categories. Maybe the three categories I'm targeting is like rural, suburban, and urban, just for the testing purpose. Then I'll create a mask called suburban, and this mask is going to be like if something like this. So let's say nums is less than 0.33. Okay, or maybe it is greater than 0.33, and nums less than 0.66. Okay, so this is the suburban mask. Okay, and then I'm creating another mask, which is, let's say, mask for urban. Okay, and here what I'm doing is this condition is nums greater than 0.66. Okay, Don't worry if you're not able to understand or relate to as to what these variables are going to do, but you will come to know. So don't worry. Right now, what I'm going to do, create the new column. Okay. So this new column, what I'm going to do is that I'm going to say advertising and create this new column target. I'm going to say targeted geography. Okay. Right. This is the new column that I've created. I'm going to put all the values as rural. Right. All the values as rural. Just like we did earlier, we put all the values as small and then we converted things to large. Like now, same thing. I'm going to say, okay, that in this data set, okay, what I'm going to do. Sorry, I shouldn't have got rid of it. What I'm going to do, I'm going to use the lock function, and I'm going to use the first mask. Let's say the suburban mask suburban, and I'm going to say I need this value to be put for targeted geography column. Okay, I needed this value for the targeted geography column. Oh, I'm sorry, I'm using a wrong bracket. Sorry. This will be this bracket, right? And the value is going to be, let's say, this is because this is a suburban mask, so I'm going to say suburban. Okay, and then the third line will be, I'll just make a copy paste so that I can save time. Sorry, Control Z. And here I'm going to say urban, and I'm going to take the mask for urban. Okay, so as you can understand, what I'm doing is just let me complete the code, then check the sample data. So advertising head 20, right? So if I execute this, my job is done. And what I've done actually is, oh, sorry. So I can do this, yeah. So what I have done here is that I've created a range of numbers. Again, the same that we have done earlier, right? We have seen the range of numbers that we have created earlier. So in the similar lines, we have created a range of numbers by setting a seed. This is going to keep my randomness constant. Okay, so to keep the randomness constant. Okay, this is to say that if I am going to run this code again and again and again, the randomness is not going to change, right? Then what I'm going to do, I'll take a mask for suburban. I'm defining suburban cases where these numbers, the range of these numbers are within the range of 0.33 to 0.66. Okay, within, not inclusive. Okay, it is not greater than, equal to, and less than equal to, right? It is greater than and less than. So it is within, right? Or you can say between. And then I have mask urban, which is greater than 0.66. Then obviously mask rural becomes anything less than 0.33, right? So that is what I'm not really going to define, because I don't need that. When I created this new column targeted geography, I gave all the rows a default value of rural, and then I'm going to use this lock function, or I'm going to use this lock method to simply mask, or to simply wrangle the data, or to replace the data, where for this column targeted geography, put the value in this column for all the rows equal to suburban, where you are able to match this criteria, which means wherever you have a true for that location, or for that row, or for that index of the row, you change the value to suburban. And in this case, it's going to change the value to urban, right? If I look at the data, this is how it has actually distributed it. So clearly, if I look at targeted geography, I'll just quickly confirm. Okay, quickly confirm the classes of new variable or a new feature. So I'm going to say advertising, and then in third brackets targeted geography, and I'm going to say, just like yesterday, value counts. And if I do a value counts, it should be able to tell me something like this. Okay, so the division is not really, I mean, the distribution of the data is not really equal. I mean, I've not divided 200 into 3 equal parts and done that. It's entirely random, and it's fine. I mean, it's not that urban, the count of urban cases is like 100 and the count of rural cases is only 2. That would have caused a kind of a disbalance in the data, which we will later see as well. It's like one class is available more than the other class. That causes a lot of problems. Okay, so we will see such kind of problems, especially when we are doing classification kind of problems. But in this case, at least, we have not created such a difference, right, or such a distance between urban and rural, or urban to suburban, right? So we have three categories now. Because I have more than two categories or more than two classes, I'm sorry. Hence, I'm going to use the one hot encoding technique. And to do one hot encoding, let's do one hot encoding. Okay, let's do one hot encoding using Pandas data frame APIs itself. Okay, let's not try to use anything else. We'll simply use Pandas data frame and the APIs it provides. We have imported Pandas as PD, so we are simply going to make a call with some function PD dot, right? And the function name is called get dummies. So it will be something like this: get dummies. I'm going to use this function to create the dummy values or to create the one hot encoding. Okay. Now you may need to pay a little bit of attention here. So what I'm going to do is that I will first of all uh, create the dummies or the dummy columns. And a very easy way to create the dummy column names, right, is to use this get dummies thing and to create the values. And how I'm going to create the values is that, okay, I'm going to use this and I'm going to say I need just another array, okay, which I can call area underscore dummies. Okay, area underscore dummies is my new array where I'll call this pd.getDummies, and inside this, now you have to pay attention. What I'm doing here is I'm passing the variable that I'm trying to convert into dummy values, right? And then I will be doing a prefix. Okay, so I'm going to say prefix is equal to, I will tell you why I'm doing this prefix. Uh, targeted, okay, targeted geography, right? Targeted geography, and at the end, I'm going to say ilock. This is a new function I'm using. And inside ilock, again, I did the same mistake. I don't know why I'm doing this again and again. Inside ilock, what I'm going to do, I'm going to say, I don't want to select any rows, okay, or any specific set of rows, but I want to select, okay, one column, okay, and that column is at the end of my list. So exactly what I'm doing is I'm specifying using this ilock the location of the rows and columns combination for targeted geography column. So usage of ilock function, and you can read more about this, is also to do the data wrangling similar to the lock function. But ilock is more flexible in terms of the fact that you can give row column kind of a combination for a multi-dimensional kind of data. So it is a bit more flexible, but at the start it is a bit more complex, right? When we start, it becomes quite complex for us, but over a period of time it is very easy for us. So it takes two arguments. This is the row argument and this is the column argument. Okay, now the row value, or we also call it row value and the column value. So row value and the column value, what it does is it simply gives you the ability to slice the data, similar to what we have already done earlier, if you remember, when we used to uh, uh, take a list, right? Take a list in Python, and if we are going to select specific rows and columns, we used to use this. But in case of a list, we only used to have a single colon to determine how many rows, how many columns we want. Here we are defining rows and columns using comma, and then we are taking the individual subsets. No, but you can also read about this. So if you simply search for pandas ilock, you'll be getting a documentation, and you will be able to understand what it is exactly doing. It is, the name is ilock because in case of lock, I was not providing any numeric value to represent the rows and columns. In case of ilock, I'm actually providing an integer to select the position. That is the only difference. Okay, but because I'm providing an integer, now I have flexibility. I can play around with the row number and the column number. Okay, so what I'm doing here is, this is Pandas data frame iloc data documentation, where it is saying it is a purely integer location based indexing for selecting by the position. Okay, it's primarily integer position based, but can be used with the Boolean array as well, right? So you can see the examples over here and you can try to understand what is going on, and then you should be able to understand what is here. So let's say here the user is creating a dictionary with a list of 3 dictionaries. Actually, this is not a dictionary, it's a list of 3 dictionaries. So I have a dictionary like this, I have a dictionary, this one, and the third one. Then he's converting it into a data frame called df, and then the data frame looks something like this, right? This is a very common way of creating a data frame out of a dictionary or out of a set of the dictionary, right? Now if I want to index just the rows with a scalar integer, then what I'm going to do, right, is that I'm going to pass this iloc function with no colons. Okay, I just want the first rows, right? So exactly what I'm doing is if I pass 0, you see what is happening. It is doing a transpose. The ABCD was the column names. Now it has transposed it. And what I am seeing over here are the values for ABCD. So it is taking the 0th row, right? That's why this is called indexing of rows. I'm passing only one value. It means only the rows, right? If I would have done, okay, the same thing like this, right? If I would have done the same thing like this, if I would have given 2 brackets, the output is still the same, okay? But it is just the reverse output, you see. Now this output, okay, this output over here looks exactly like my original data frame. Hence, the type of this output is also a data frame, right? But in this case, it's a series, right? Now, if I want to do a slice, I'm going to use things like this. I can also use lambda functions within it. It's not quite easy. I mean, at the first place, you may not understand what exactly I'm trying to do. Maybe over a period of time, with more and more practice, we will come to know. But the only thing that iloc adds as a value is that during your data wrangling stages, you are now able to use integer based wrangling techniques rather than location based wrangling techniques, because in lock you are using locations. You have to identify the location using the text, using the keyword, or using the value. Now you don't have to. Okay, so that's the advantage, because of which it gives you a lot of flexibility to play around. You see what is happening over here. This is exactly what I'm doing, right? This is exactly what I'm doing. What it is doing, slice objects. It is doing a slice object. So what it is doing, 1:3, right? 1:3 means give me the rows or all the rows of the data starting from, okay, starting from row number 1 until row number 3, exclusive of 3, right? So if you remember the list subsetting things that we have learned, 1:3 means row number 1 and row number 2, 3 will not be included. So it has given row number 1, row number 2. Then where did the 4th column go? The 4th column went away because of this, right? I have selected what, 0 to 3, right? 0 to 3 I have selected. It means column 0, column 1, and column 2. In the same way, what I'm doing over here is I'm selecting the first column here. Okay, the first column is this. Okay, what I am doing, I might be doing it in the opposite way, so that's why you may have a confusion. But you can do one thing, or we can do one thing, is that we can simply run this and we will be able to see what is happening over here. Okay, so what we are doing is we're taking, or we are creating a column, and then we are taking this value, targeted geography, from our data frame. We are giving it a prefix. The prefix is this, right? The prefix is this. Okay, if I change this prefix, it is going to change as well. You see, if I change the prefix, this part is going to change. How am I going to call? And then this part is not added by me. This underscore suburban or underscore urban is not added by me. Why is that done? That is done because it has already added the value. Now see the magic of iloc. Why did I use iloc? If I remove iloc, right, it has actually created 3 columns. Right, it has actually created 3 columns. Right, I am intentionally removing 1 column. Intentionally, I'm using iloc to remove 1 column. So if I go back again, okay, if I go back again, remember this output. I'm seeing rural, suburban, and urban. If I run this, sorry, if I run this, I am not going to get the rural part. I'm selecting from the first column and the second column of the previous output. Why am I doing this? I shouldn't have used this iloc. I needed a data frame, as I told you during the explanation, that if I have a column which has three values, let's say A, B, and C, I want to do one hot encoding, then ultimately I need C1A, which is a column, C2B, which is the second column, and C3C, which is the third column. And then I should have values like 100, right? So in this case, it will be something like 100, 010, and 001, right? I hope you are able to understand how one hot encoding works. Now, what we are doing essentially, or what I am doing is that, let me take a different color. I am not taking one of the columns. In this case, the first column. You can ignore any of the columns. That's up to you. Up to you. You can slice and dice, and you should always take only two of these columns. Why is this the case? Again, I'll go to the definition of degrees of freedom. If you remember, I have three unknowns. If you remember the definition I gave you earlier, I have three unknowns. I have three linear equations. How many do I need to solve to find the answer to the third? I don't need to solve all the three. If I solve the first two equations, I get the values of, let's say, x and y. If I solve for x and y, I don't need to solve the third equation. I simply impute the values of x and y into the third equation to get the value of z. In the same way, I don't want to confuse the machine learning algorithm or the statistical implementation or the inferencing by passing all the encodings or all the values. If I only pass the degree of freedom, in this case I have how many? Three columns. The degree of freedom is 2. If I only pass two columns, my job is done. Automatically this becomes the opposite. Are you getting my point? So automatically the third value is assumed by the calculation. So that's why I don't need to give the entire data set to the machine learning algorithm. I have to limit this only to 1 and 2. Any doubts in this? Any doubts? No, right? Okay, there's a chat. Okay, yeah, okay. So we have created this. Let me just put this in this variable, and then in home I'm going to just remove this. And what I'm going to do now that I have got these two columns, I have to add these two columns as well into my data frame, right? I have to create a complete, let's say, data frame so that I can work on it. So how do I do that? Very simple technique. Now I'm going to use another function, PD pandas. I'm going to use a function. Give me 1 minute, friends. I'll be back. Yeah, give me 1 minute. Sorry, friends, I'm back. So We will be using a function called pd.concat, and pd.concat is usually used to merge, or I usually use that to merge one or more data frames. It is a very, very useful technique, but it is not used always to merge the data frames. There are other merging techniques like join and so on, things which we have not seen earlier because of obvious practical reasons, that if we would have seen it earlier, we wouldn't have got the context of why or where concat and other functions are used. That is why we are introducing so many functions. I hope you don't mind. uh, so these are functions which are really helpful, but other than contact, there are other than concat, there are other functions like merge and join also that we are going to use later. But what concat does is it simply assumes that you have the same size, same scale of the data, same size of the data, same number of rows are there, and it's going to take two data frames and join it together without any concept of primary key or something like that, if you're coming from a database background. So let's say I have an employee table and a department table in any database. And as of course, after we are done with the regression analysis, we will be looking into MySQL database, because we have to look at SQL programming language and its usage to do data science. Now, in this case, if let's say I have employee table and the department table, there must be some kind of a key field between these two tables so that I can join them and I can find the output, right? But in case of concat, it does not expect you to give any key. What it is doing, it is taking a data frame which is of some size. Okay. Okay. So it is taking a data frame of some size, let's say 2 cross 3. Okay, 2 cross 3 it has. So it has 2 rows and 3 columns. Okay, it has two, yeah, it has 2 rows and 3 columns. And then there is, let's say I have another, let's say data frame, which has 2 rows, okay, but 5 columns, right? So because the number of rows is the same, so I can clearly concat this. So I'll do a logical plus, which means now I'm going to get a data frame, which is a very big kind of a data frame, which is going to have 2 rows, okay, and 5 plus 3, 8 columns. Okay, this is what this concat function is going to do, right? So that's exactly what I'm doing over here. I'm going to say pd.concat, and I'm going to concatenate both of my data sets. So what I'm going to say here is advertising now has to adopt, it has to change, it has to be advertising, okay, concatenated with area underscore dummies. Okay, so area underscore dummies is already a data frame. Okay, I'm joining that data frame with this data frame because I know that the number of rows in both the data frames is equal to 200, right? Now, how am I going to join them is something I have to pass, right? I have to pass that. So to pass that, what I do is I pass the name of the data frames within third brackets. Okay, within third brackets, I pass the name of the data frames. And then what I say is that comma axis is equal to 1. The axis equal to 1 means I want to join by the columns. Axis equal to 0 means I want to join by the rows. If you just saw my example in the diagram that I've drawn, 2 cross 3 matrix or data frame got concatenated with 2 cross 5 uh, uh, matrix, resulting into a 2 cross 8 matrix, right? So I concatenated basis of what? The value that increased, right? Which value is going to increase? The column is going to increase. So axis equal to 0 in pandas means rows, axis equal to 1 means the columns. This is a constant thing. This axis value will be 0 for rows, will be 1 for columns across anything you do into pandas. Okay, please remember this. In any operation that you do with pandas data frame, if you are specifying axis is equal to 0, you want to do the operation basis the number of rows. If axis is equal to 1, then you're doing the operation impacting or basis the number of the columns or basis the columns itself, right? So that is exactly what I'm doing over here. Let's try to do that and let's try to see what we have resulted into. So I'll see advertising dot head again, and I'm going to say, let's say 20. So if I do this, this is what I've got. I have got my previous columns. Obviously, I've not done anything with them. And then I have got the targeted geography suburban, targeted geography urban, right? So this is what I have already got. Let me just take the names of the columns once. Advertising advertising dot columns. I'm just going to run this dummy cell so that I can take these column names, and then what I'm going to do, I will come back, and now that I have implemented one hot encoding, I can safely create my model, my fifth model in this way. So I'm going to use sales is TV, radio is large, SK was already there, but it was not adding any value. Maybe I'll remove this and I'll say targeted geography. Targeted geography is what I'm going to use. And here I'm going to use this. So targeted geography urban, I'll just copy, paste it over here, and plus targeted geography suburban, right? So I'm going to call this as suburban, SUB. Okay, and the data is advertising. I'm going to fit it, and then I'm going to look at the summary for my fifth model. If I look at the summary, let's see what is going on over here. We did not add any value, by the way, because these are entirely dummy variables. But I just wanted to show you that we are actually able to fit the model using the one hot encoding as well. And we are able to get the coefficients, as you can see over here. But our p-values are really insignificant, obviously, because these are dummy columns, right? These are entirely dummy columns, has no relationship with the business, and hence the p-value may almost always be irrelevant for us. So the exercise here was just to show you how to do one hot encoding. It may or may not really have an impact on the model itself, but we do see a small change over here, which is the p-value e to the power minus 98. Earlier, if I remember, it was e to the power minus 99. Let's just quickly cross check. You see, it was 4.27 e to the power minus 99 earlier. Now the value is 9.68, but e to the power minus 98. So the value is a little bit more, very, very small amount is more than the previous value. Doesn't matter. Okay, it doesn't really matter. Our overall model is good, but the overall model is good because our p-value is much less, right? Our p-value is much lesser than the alpha or the critical value, or the significance level. I'm sorry. Uh, but these two columns are not adding any value. Clearly, we can see that from the p-values, right? I mean, from the p-values, we can clearly see it is not adding any value at all, right? But this was just an exercise. This is just an exercise to tell you how one hot encoding actually works. Right now, I think you can understand what is the effect of doing one hot encoding. So let's say in my targeted geography column, I had unique variables number 3. So I have resulted into, obviously I have trimmed down one column because of the problem that I was actually mentioning. So that's why I have reduced it down to only 2, right? So it's like if I have 3 classes, I should ideally result into 3 minus 1, and that is 2 extra columns. So imagine if you have a categorical variable which can have 40 unique values. Okay, if you have a categorical variable with 40 unique values, obviously you're going to result into a data set which is going to now have 39 extra columns added to it with zeros and one, zeros and one, zeros and one. It's going to be a very, very huge data set. Really very huge data. And from that data to find out relevant fields which are adding value to the model is a task, is a daunting task. But as I've already informed in one of the sessions, there are methods to do factor analysis. One of the method is principal component analysis, by means of which at later stage we will be reducing the number of these so-called columns from 39 to maybe 3 or 2, right? To the number of columns, we are going to restrict ourselves to only those number of columns which are actually adding any value to the model and are not like these 2 columns that I have taken in the model, right? Which is really, I've just added them just to show you the demonstration, but it is not creating any good thing for me. I mean, this field or even the earlier field, right, is large SK and is large, did not really add any statistical value. It did not add any value to the module, right? Now, before we close, let me just quickly also tell you what is a quick name of the a technique that we have done. So I'll just quickly write some notes and then we can make it a close for today. So point number 33, if we have if we have p number of distinct classes, right? P number of distinct classes in any categorical variable, and we apply, okay, if we apply one hot encoding, we result ideally, okay, ideally we should result into P minus 1 columns by removing any one column, okay, any one of the P of the P columns. Okay, we are removing any one out of the P column, similar to what we have did here also, right? We had three values, we removed one, right? So we removed one, we are left with P minus 1, which is 2. By removing any one of the P columns, this technique, okay, is also known as uh, handling dummy variable trap. Okay, dummy variable trap handling is what this is known as. We have simply made use of the same concept as degrees of freedom, right? I think we don't have time now. Let's make a stop over here. We are going to continue tomorrow. Yeah, I'll stop my screen sharing. Thank you so much, friends. Thank you. Thank you. Good night. Thank you so much. Good night.